And last but not least, we've got one more TechTalk. We've got Dr. Julian Bachmann, who's the co-founder of ATLANT 3D, joined by his master student, Micah Mc Naire, who will be talking about how it all started and how it's going, so from a nozzle to fully printed solar cell stacks. So if you could welcome them here today.
Recently, we've had quite some new successes with the ATLANT technology in our lab, in academia, on the other side, if you want, in Erlangen, and this is why Micah has joined me so that he can present his own results, because he deserves it. But I thought that because it's been so nice these past 6 months, I should also put that in perspective and show where it started, and that it doesn't happen in a day, and that it takes a lot of work by a number of people. So for most of you, this is what DALP looks like. We tend to call it ALAM in our papers because that's how we called it in the first paper. That stands for Atomic Layer Additive Manufacturing. I guess it's a subsection of DALP, right? DALP would be the more general description. That's what it looks like, and you perhaps take it for granted. But that's not how it started for me. It actually started this way here. This was an event by an EU network where I was invited to talk about career. That was one of the first times I was invited as a senior, to talk to the youngsters about career. And yeah, you can see me here and you can see Ivan there. Oddly enough, this picture was taken of me when I presented a little bit my take-home messages for how to build a career. And one of the take-home messages was recognize and catch opportunities. And it's a bit odd that at this very event, such an opportunity was offered to me in the form of Ivan talking to me about this idea of this nozzle that laterally constrains ALD chemistry, and where I thought this is the most amazing idea that I've heard of. And I did catch that opportunity, and here we are today, right? That to me, that's a bit amazing, and that's how it started with this idea of the nozzle controlling the gas delivery, and we built our first. Well, you think you're going to make the minimum viable product. I don't think that that's what this is. It might be the minimum viable prototype, but you're laughing. It's got everything you need here. So on the left-hand side here, you see the ALD precursors, right? You see some control valves. You see the head here with the nozzle above the motion stage that holds the sample, and some vacuum system on the right-hand side. So it works, and that's how we did our depositions for a few years, and we still use it, and it still works. And with the colleagues in Bratislava, we not only demonstrated for the first time that you could change the length of lines and the thickness of lines and make gradients, but then applied it for the first time to a prototype where you had a sort of a quantity to achieve, namely the 100 ohm that you want to have at room temperature for a PT100 element, and you could actually use this type of approach to find the geometry that would give you these 100 ohm, right? And then we also expanded the chemistry, and here, for example, we demonstrated that basically anything that works in ALD, you can use it for DALP. We did this very systematic study of all the process parameters for ALD with a certain type of new precursor, and then in DALP, and we found that everything follows in a very parallel manner, that even the material parameters, as they vary with temperature, vary in the exact same way in ALD and in DALP. And that means now that that this whole range of ALD chemistry you can use in DALP. It's all there. Your consumption of precursors in terms of sustainability is several orders of magnitude lower, which is a good thing, but you have all that chemistry at your disposal. And then, of course, this simple first prototype is limited in terms of what we can do. So we built this second prototype for being able to now make multi-material devices as opposed to just one line of one material. So you see that now we've got a system with a number of precursor delivery lines on each side that you can switch between and purge between. We put the whole thing into an air-free enclosure, or sort of air-free. The stage is also faster and larger so that we can actually move around a bit more, also between switching precursors. And yeah, I don't think it looks pretty. It's complicated as it turns out, as we had to learn. But if you look at the core, it's still the same thing. It's still the same nozzle. Actually, physically, it's the exact same nozzle, the same delivery head, the same technology, the same thought. And basically, this is what I showed to Micah 6 months ago when he started his master's thesis. I said, I would like to be able to print what we've talked about today, right? A pattern or a platform where you print a certain device several times while varying a certain parameter. And because there are certain applications that are already done here at ATLANT, we wanted to do another type of application, namely here solar cells. And I would like to have an array of little solar cells where you vary a certain parameter and you investigate what the properties and the performance look like. And others had failed before him, and within 6 months he actually collected a whole variety of results, which I think he should show you, because he should be known to this community, because I can say that he's going to make a splash in this community. So go ahead, Micah.
So yeah, what Julian already told you is that I investigated how can we manufacture solar cells using DALP, or I just call it ALAM because I'm more familiar to it. So, and I specifically investigated this solar cell stack, which employs a zinc sulfide adhesion layer with the antimony sulfide absorption layer and a vanadium oxide whole transport layer, all to be manufactured in a 3D printed way. Of course, then this necessitated us to figure out ways how we can deposit these materials with sufficient material quality. So I first investigated the vanadium oxide printing. This was actually quite straightforward, was definitely the easiest material to do, as it already uses a established vanadium oxide ALD method of VOTIP and water, but now in a 3D printed format. And yeah, the results were quite amazing. So we were able to really print very defined lines of vanadium oxides. And using now a 3D printing method, we can also take advantage of the direct patterning capabilities of DALP. And here, for example, you can see a 15mm long line with 5 segments of different layer thicknesses. And you can now, for example, take this one sample and scan this using imaging ellipsometer, and you can obtain growth rate information by just one single sample. So what otherwise would take you multiple days, if not even weeks, in conventional chamber ALD, this can be done in just one single day, which is quite amazing. And furthermore, everything else that we see in conventional ALD also transfers to our setup here, or to this experiment here. So we get around 350 micron wide lines with exceptional surface morphology, so you can't even see it in SEM anymore. It's that smooth and conformal, and exceptional composition impurity, as well as a high crystallinity of the material. So this is basically exactly what we want in terms of materials that we later want to use for solar cell fabrication. Then I headed over to the zinc sulfide atom printing, and this was far more complicated. So first we had to use a completely different precursor. Normally you use diethyl zinc in ALD, but this was not feasible due to the high vapor pressure. So we switched out the precursor and did a whole through optimization of this new system. But still we were able to, again, print very defined lines of zinc sulfide with a zinc sulfide base layer. However, you can also see, unfortunately, that there is some agglomeration visible on top of these lines. We then further investigated, okay, what is this? And we found out that we actually have a really compositionally pure zinc sulfide base layer. However, we still have problems with the precursor reaction. So there is unreacted precursor on the surface, which then oxidizes upon air exposure. Nevertheless, the underlying zinc sulfide layer again showed a crystalline structure of zinc sulfide, as well as self-limiting ALD growth behavior. So again, exactly what we want for solar cells. Then heading over to our most important part, the light absorption layer, the antimony sulfide. Here again, we use a well-established antimony sulfide ALD method of TMASB in combination with hydrogen sulfide, again now in a 3D printed format. And noticeably here is that we actually had to cool down our precursor quite a bit because of the high vapor pressure in the system. So this also necessitated us to construct a whole bubbler cooling system for that to selectively or target exactly this temperature. But despite these hurdles, again, we were able to print anti-monosulfide lines, very defined actually, but with one restriction. And that is, if you print this on a silicon wafer, you can see that the as printed film shows island growth and pinhole generation. And it even gets worse when you anneal it, it completely de-wets. And this is quite unfortunate because everything else in terms of composition impurity, in terms of crystallinity after annealing, and the self-limiting ALD behavior is up to par that we want for our ALD materials. But now we can just combat this de-wetting by combining the antimony sulfide with a zinc sulfide adhesion layer that we've established before. And if we combine now these two methods and we do a 1 nanometer thin zinc sulfide layer underneath the antimony sulfide before annealing it, then the difference is night and day. Now, after this 1 nanometer adhesion layer of zinc sulfide, you can get very smooth and conformal layers with defined structures and grain boundaries. So this is exactly what we want to have for our solar cells. However, small restriction here is, again, unfortunately, the zinc sulfide agglomeration causes some holes and impurities in the layer. So this is, of course, then something we want to investigate in the future to also eliminate this. But now we basically have everything in terms of materials. But now we have the problem of feature sizes. So the feature size of DALP is quite lower, of course, compared to uniformly coating something in ALD. And therefore, we also had to rethink our design of the solar cells. And what I came up with is a design that is still pretty close to what we use in ALD studies, so we can connect it quite easily to our solar sim, but we had to do multiple modifications. Foremost, we had to reduce the active window size to a merely 0.5 times 3 millimeter size, so this is very small. And of course, by reducing this active window size, you also run into problems of potential short circuits between your ITO and your gold back contacts. So then we also furthermore had to place the gold back contacts as well as the alum prints in a very specific manner on the ITO substrate, on an ITO edge, so that any short circuits can be prevented. But of course, this increases the manufacturing complexity. This design still allows a rather small alum printing area and thus way faster prototyping. And of course, the most important argument here is that you can fabricate 6 solar cells with 6 different configurations on a single substrate, which is of course not possible in conventional chamber ALD, where you unilaterally coat everything. So these different configurations are simply not possible in the system. But then, okay, we had to figure out, is this even possible to do this manufacturing in such a precise manner? So first we investigated, can we place our gold back contacts on such a precise manner on a precise ITO edge? And we actually found out, okay, this is quite simple. It can be done even with a just rudimentary gold plastic foil for masking. So, okay, this works out great. And basically now we have everything, and we started to actually manufacture these solar cells by precisely alum printing these different layers exactly on the structures as we want them. And the outcomes, I think, is pretty amazing. You can clearly see the structure of the alum print specifically placed on this ITO edge, with the gold back contacts also precisely placed on this ITO edge to prevent any short circuits between the underlying ITO. And not even that, we were able to fabricate 18 solar cells with 3 different antimony layer thicknesses on a substrates in just 1.5 weeks. So not only were we able to boost our configuration prototyping, but also increase the throughput quite a bit. And what is even more amazing, they actually work. So of course, they're not completely pretty, but you can clearly see a photocurrent present when measuring them in dark or then in illuminated conditions. So we were able just to transform basically line material deposition into functional devices with minimal additional steps, which is quite amazing. Of course, this is a proof of concept solar cells. So this was specifically designed to use as low manufacturing step as possible to be as cheap as possible, basically. So we still suffer from low performance of these solar cells and, of course, issues with reproducibility. In fact, only a small fraction of the 18 solar cells that we printed in 1.5 weeks was actually functional. However, this gives us quite a confidence boost that we can, when we address these issues and improve further the alum printing methods, that we can try many different materials as well as layer stacks and also geometries in boosting the PV community and the PV research.
Yeah, thank you, Micah. So can you imagine that? That's a 6-layer device stack, right? Or a few years only after these original ideas and these original prototypes. So I think it's been a long way or we've gone a long way in a short amount of time. And of course, there's a lot of technology involved, but the most important aspect, as you have just perhaps noticed now, is the people. So it takes a leader, right, to just keep adding. So thank you, Maxime, for that part. It takes a very special engineer to actually imagine this nozzle, which is very complex in three dimensions. So thank you, Ivan, for that. It takes the whole team of engineers here at ATLANT to, in the end, simplify, beautify, make it all into a machine, which in the beginning was not exactly a machine. Thank you, ATLANT, for that. And on the academic side, it takes the hard work and the enthusiasm of the scientists and students to establish all the chemistry that is all behind these applications. So thank you to the people who in Erlangen have contributed to that. Most importantly, Ivan, Sarah, Yara, Sonia, Sanya, and Mika. You see that the letter A is important in the first name of the people involved. That's probably because they work on the ATLANT machine, I guess. There's also some funding involved. The European Union funded us and funded common project between FAU and ATLANT for a number of years. This is the rest of the team as it stands now, working on other topics. And I would like to also mention that very recently we obtained a big batch of funding on more on the fundamentals of ALD surface chemistry in Erlangen to be done in a large consortium with a number of groups working more on in situ characterization and theory and applications of ALD from the gas phase and from the solution phase. So thank you very much to you for the work and to you for your patience with us.
Thanks, Julian. Thanks, Mika.